Thank you. And yes, I'm going to tell you about our project called Deterministic Client. So here at OSDI, we all like fault-tolerant systems, and a common way of implementing fault-tolerant systems is through the use of a replicated state machine. And here, each replica is going to maintain a local copy of a state machine, and then uses a deterministic function to decide on the next state transition. And thanks to the determinism, each local replica stays in sync with all the others. Now, we also like extensible systems because they allow flexibility and don't impose policy on the user of the system. They can sort of provide their own programs to customize the behavior. And so you see this all over the place. In your web browser, you've got JavaScript. In your kernel, eBPF. And maybe in your text editor, Lua. And the core primitive to enforce that these user-provided programs maintain the guarantees that the system needs is through the use of a sandbox. And so when you put these two things together, an extensible replicated state machine, what you get is what's generally known as a smart contract. And so here, these replicas are now going to be running some user-provided program to decide, or as a part of the function that decides the next state transition. And because of that, these programs additionally need to be deterministic, not only isolated and preemptible, but also deterministic. And this additional requirement changes how we need to also implement isolation and preemption. Now, existing systems that do this are kind of slow. So you can use a JIT or an interpreter, and there are various overheads compared to running native code. And this can result in high metering fees when you try to run expensive programs in these systems. So let's look a little bit deeper into how these existing systems work. Usually, you have some source code input. You compile it with some ahead-of-time compiler to an intermediate language. And then you use some sort of trusted compiler to turn that into machine code. So maybe a JIT compiler or an interpreter to run it. And this stage here is really where the overhead and complexity comes from, right? JIT compilers are highly complex, hard to get right in a security-sensitive situation, and have overheads compared to native code. And interpreters are much slower, and these are actually the standard in smart contract engines. So the question is, why can't we just directly run the output of LLVM, right? LLVM gives us highly optimized machine code. Why can't we use that for our smart contract? And there are four, maybe three overall problems to this. When you take an existing program, if you have a program that expects a Linux API, it's going to have all sorts of non-deterministic things in the API, like clocks, parallelism, the ability to spawn multiple threads, maybe make network calls. And so lucky for us, this first problem is sort of, we're going to cop out, and the programs we're trying to run are already built for smart contract engines. And so there's already a deterministic API that's enforced, and we're not going to worry about this. We're going to assume that the runtime provides a deterministic set of functions that's not like a Linux syscall API. And one thing to note here is that there's no parallelism, so no ability to spawn multiple threads. The next things dive a bit more into the details of the system, the machine. So there are actually hardware instructions that are not deterministic and can't even be trapped. So the first one, read TSC, this can be trapped. I mean, you can set a configuration to disable this, but it's sort of a general example, something that just reads the timestamp counter that's going to give you a non-deterministic value. These next two are a little bit more difficult. So this is just a standard conditional jump instruction on x86 that's jumping based on the 0 flag. But it turns out that the x86 architecture allows the flags to become undefined at various points. So certain instructions place the flags in an undefined state. And that means that this instruction, if the 0 flag is undefined, it can, this jump can either be taken or not. And if you look at different microarchitectures, like from Intel or AMD, they actually do different things. When you run an instruction that sets a flag to an undefined value, sometimes it'll be set to 1, sometimes to 0. And then on ARM, this is an example of a load instruction on ARM that is specified by the ISA to be unpredictable. It can put any value in the X0 register after running this instruction. Now, there's also a problem with preemption. We don't want to allow the programs to run forever, and the usual mechanism for this is a timer interrupt, but that's not deterministic, so we're going to have to do something special to handle that. And the last case is when we want to run multiple sandboxes in the same address space so we can run them as part of a Linux process. We need to make sure that, if we're loading them at random places in the address space, the sandbox can't see addresses related to that because that's a source of non-determinism. So DeCl is this project for enforcing all these types of determinism. And we support x86 and ARM. These are separately supported. And for this version, where we consider floating point to be out of scope. So there are some runtime requirements I'll briefly mention. First, we separate code and data. So the runtime is, again, not going to allow you to have a page marked as read, write, execute. And when we start up a sandbox, we're also going to have it be 0 initialized. So the register state is initialized to 0, and any of the virtual address space that's not used by the code or data is unmapped and inaccessible. Now, if you're familiar with SFI systems, this overall architecture probably looks familiar. So we're going to have a modified compiler, special version of Clang that does some rewrites at the assembly level, at the machine, or the .s file level in the compiler, and then it produces some code that's been rewritten such that it's verifiably deterministic. So there can be some static analyzer that comes and looks at the code and says, yes, I'm sure this program is deterministic, and maybe I'm even sure that this program can be preempted, it won't run forever. Or if it gets something that it's not sure about, it'll reject the program. And so these rewrites ensure that any program you send through this compiler generates something that passes verification and then can be just run natively without any further translation. So the first thing we need to do is we need a mechanism to allow our verifier to inspect every instruction that's going to run in the program, and so that it can restrict the program to some allowed set. So maybe it's never going to allow that non-deterministic load or that unpredictable load instruction on ARM. By the way, for the rest of the talk, I'll mostly have examples for x86 because there's a little bit more complexity there, but you should see the paper for the information about the ARM version. So on x86, to do sound machine code analysis, we need the technique of aligned bundles, which is something that's commonly used in classic SFI systems. So, for example, native client. And the idea is that we're going to make sure that no instruction can jump, no indirect branch can jump into another instruction, because then it could execute an entirely new sequence of instructions that our static analyzer, our decoder, did not analyze. So the way we do this is we say no instruction can span a 32-byte boundary. We're going to pack instructions into 32-byte bundles. And then if one instruction were to span the end of the bundle, we just pad with no ops and start at the next bundle. And then all jump targets must also be 32-byte aligned. So if we look at this program actually, if you actually compile this, it'll run a read TSC instruction, because even though each individual, this move looks deterministic, this LEA looks deterministic, but then this indirect jump is actually going to go into the middle of another instruction and execute something that we didn't see. In order to prove to the verifier that this jump target is bundle aligned and therefore doesn't go into the middle of an instruction, the rewriter needs to include an additional instruction here that's going to perform a mask where it zeroes out the bottom 32 bits of the target. And as a result of that, the verifier can now be sure this target is some bundle aligned thing. As long as it can see no instruction spans a bundle boundary, then it's not going to go into the middle of an instruction. I'll just point out this isn't actually necessary in ARM, and this is one of the nice features of ARM, is that fixed with instructions make this unnecessary. So getting back to the example of the jump of 0, right? The E flags register can have undefined values. So the divide instruction is one example of an instruction that puts every flag into an undefined state, every arithmetic flag. And so if we have, we look at this, we look at the jump of 0, and now this is reading some undefined value, so it could be non-deterministic. So we need to have a rule that the flag must be set to a defined value before it's used. And there's a bit of a difficulty here to guarantee this across basic blocks. So there are two cases. One is basic blocks from indirect jumps. We actually don't know what those are at the machine code level, but luckily this AND instruction we had to introduce before every indirect branch for bundle alignment anyway defines all the arithmetic flags. And so no matter where we arrive, we're guaranteed to have some deterministic set of flags from indirect jumps. Now for direct jumps, since they're statically analyzable, we can construct a control flow graph, and we can statically verify that that between when a flag is set and when it's used, it's never set to another undefined value. And more precisely, like when we use a flag immediately or in the same basic block before, the flag was set. And in some cases, we allow analysis of up to one basic block away, a conservative data flow analysis to allow basically certain types of if statements that LLVM produces. So there are a couple more details that I'll skip for time reasons, but You should see the paper for those. So next, we're going to look at how we do deterministic preemption and handle the multiple sandbox case. So first, I'll tell you about two forms of metering, branch-based metering and timer-based. And then after that, our solution for multiple sandboxes called position-oblivious code. So in branch-based metering, we can't use a timer interrupt, right, because that's non-deterministic and could preempt the program before some side effect on one replica and after some side effect on a different replica. And so instead, we need to keep a software count, basically, of the number of instructions that has been executed, because that's a deterministic value. So we keep this in a reserved register called R12. The verifier ensures that R12 is never written for any purpose other than the enforced instructions that are needed to track the metering. And then we're going to, again, have our construction of a bunch of basic blocks. And at the end of every basic block, there needs to be a metering sequence, update sequence. So it's going to first reduce R12 by the number of instructions that executed in the basic block, and then it's going to do some check, checking if R12 went negative, and if so, performing a trap. So this is great for direct jumps. I'll just mention an indirect jump can arrive anywhere, and that's okay, because if it arrives in the middle of a basic block, it'll just get overcharged. And the program, if it doesn't want to be overcharged, can insert an instruction that subtracts from R12 if it wants. The important thing is that since this metering sequence it fits into a 32-byte bundle, it's not possible for an indirect jump to arrive somewhere inside of this metering sequence. And I'm glossing over exactly how to do this check. This actually involves a conditional branch, and that's a bit complicated because this already might be a conditional branch using the flags. So we use the one conditional branch instruction on x86, which does not use the flags, the JRCXZ instruction, but you can look at the paper for the details on that. So it turns out that this conditional branch is kind of expensive, especially if we have to perform it at the end of every basic block. So we have this alternative, this optimization called timer-based metering, where we delete this check, and instead we have a non-deterministic timer that's going to fire at some interval. And since we're still tracking the gas, we're just not checking it. What we're going to do is check the gas when the timer fires and check the gas when an external call is made, like a side effect. And because of this, the program is actually still deterministic. And it can execute, once it runs out of gas, it may execute for some non-deterministic period afterwards, but it's never able to externalize a side effect during that period, because if it ever makes an external call and creates a side effect, it is terminated instead of servicing that call. If it enters an infinite loop, at some point the timer will fire and cause it to be preempted as well. And there are no side effects from, because it wouldn't have made an external call. So finally, I'll talk to you about the, having multiple sandboxes within a single Linux process. So we're going to use software-based memory isolation for this, because this is what we have to do if we want to run within a single address base on Linux. And we build this on top of LFI, which is a classic SFI system. And basically, it works by rewriting, it sets up a sandbox region of the virtual address space, which is 4 gigabytes. And then all loads and stores in the program are additionally rewritten into an offset, a 32-bit pointer added to the base address. And since the offset is 32 bits, it's guaranteed to it can never go beyond 4 gigabytes away from the base. Now, there's this problem, which is that the program can actually, in stock LFI, can determine its base address, because it can just read its stack pointer, or it can perform call instructions, and a call instruction will push an absolute address onto the stack, and then it can inspect the stack. And since we have, we might be loading the sandbox at a random location that sort of depends on what else is in the address space, this is a source of non-determinism. And so our solution to this is to just never allow the program to read the top 32 bits of a pointer. So reading RSP is disallowed, although reading ESP is allowed, because that's the bottom 32 bits. And then also, we just completely disallow the use of call. And so for a rewritten version, these look like this, where now we're instead reading out of ESP, and instead of performing a call, the program has to manually push a 32-bit return address onto the stack, and then use a direct branch for the jump that is associated with the call. So I'll take you quickly through the evaluation. I know we're a bit behind schedule. So here's some of our evaluation on spec. This is to get an idea of what these overheads look like on general purpose C or C++ programs. Again, these are Linux programs, so these are running not with a deterministic API. This is just for benchmarking purposes. And what we can see is that the position-oblivious code is it's hardly any overhead compared to LFI, but then when we introduce the metering, that's when we start to get more significant overhead, roughly 15% for timer-based, and then 20% for the ARM version of branch-based, and 35% for x86. So I can go into more details afterwards about why the x86 branch-based metering is more expensive, but it has to do with those flags that we have to make sure to preserve. And then we're getting a nice improvement compared to the Fuel version of Wasm Time, so it's a JIT compiler that is also doing metering. We also ran some benchmarks to do zero-knowledge proof verification, which is one of the more expensive things people try to do in smart contracts. Basically, it's a lot of fancy cryptography code that is running inside the sandbox. And with DeCl, we're able to bring the overheads much closer to the native code. And this is where maybe DeCl really shines, because on a lot of straight-line code where there's not much control flow, you're really just getting the native code to run inside the sandbox, rather than having to go through an IR and incurring the overhead of that. Finally, we have an end-to-end benchmark on a smart contract system called Groundhog. And the important thing to look at here is these solid lines, which are its transactions per second, when the cryptography routines like signatures are included inside the sandbox. And so we're able to get like double transactions per second when the sandbox is performing all the work. And so if it's no longer bound to whatever the fixed API that the runtime provides is, the sandbox can use new cryptography when it comes out, things like that. So I'll wrap up here. In conclusion, when you have a replicated state machine and you want it to be extensible and you want the maximum possible performance, you get something like deterministic client out the end. Thank you.